is thorium-234. Notice this side equals this side. 238 equals 234 plus 4. 92 equals 90 plus 2. Capiche? Can you see this? Can you see this relationship?
Yes.
Even in the back? All right.
Wait.
Yes.
So mass of the nucleus is equal to protons plus neutrons?
Yes. Wait. So a decay is any time a nucleus turns into another nucleus. Nuclides that will decay are called radioactive. A radioactive nucleus is one that's getting ready to break down into something. The half-life is the time it takes for half of your particles to do something else or become something else. I think I might have bumped the camera at some point. Now it's crooked.
Wait, so radioactive nucleus is ready to change into?
There we go. Now it's less crooked. Okay. So the half-life is the time it takes for half of your particles to do something. So if there were 100 of you eating sandwiches, the half-life is the time it takes for half of you to finish your sandwiches. Okay. Make sense?
Yes.
Okay. So if you had 100 particles, the half-life is the time it takes for 50 of your particles to turn into something else. Okay. And then another half-life is the time it takes for that 50 to become about 25.
Wait, so is this half-life for the nuclide?
Yes. So if you have a radioactive nuclide, the half-life is the time it takes for half of those particles to turn into something else. Yeah.
Is half-time with half-life only for radioactive?
Oh no, it's for everything. Yeah, half-life is used in a lot of different things. But when you talk about half-life, you always see the same basic pattern. So, wow, good question. It's used in economics, it's used in physics, it's used in biology, it's used in a lot of different things. So, basically, if you had 100% at 0 half-lives, 1 half-life, 2 half-lives, 3 half-lives, 4 half-lives, 5 half-lives, we'll make this 50, this is 25, this is 10. So basically, at 0 half-lives, you have 100%. At 1 half-life, you have 50. 2 half-lives, you have 25. 3 half-lives, you got about 12. 4 half-lives, you got about 6. Then 3, then 2. You always see the same basic graph. Okay. So this is the half-life curve that you will see if something has half-life.
Isn't it quadratic?
Yeah. Half-life, the idea about half-life is everywhere. Okay?
Oh, it's
Questions? Questions?
There was something I was wondering about for a while. Like, how do you determine like the maximum or minimum number of neutrons that can be in a nucleus?
Oh, that's called the band of stability. And we're going to learn that in about 6 slides, probably tomorrow. Just a plan to see what it means, what it basically is. We'll learn it soon. Yeah, I'm sorry, we will get to it, but I want to stay on track. Okay. So yeah, we'll talk about what makes something radioactive, stable or unstable, and then we'll have a simulation on Friday to talk about it too. Okay, so alpha decay. Alpha decay is when you get an alpha nucleus or an alpha particle that is ejected. Again, an alpha particle is a helium nucleus. It is big, it's slow. Okay, it's big and slow. So imagine playing Red Rover, and you go like Red Rover, send Byers right over. And Byers is like, oh, my hip, and he's like, run, I can't break through. Do you remember Red Rover? It's like Red Rover, send the big fat kid right over. Or send the slow little kid over. So the alpha particle is like me, big and slow, can't break through. Okay, can't break through. He's like, Red Rover, good luck, send Byers over, ha ha ha. Well, an alpha particle can't break through materials, so your skin is good enough at protecting you from alpha particles. Don't swallow an alpha emitter, but if you like hold an alpha emitter in your hand, you'll be like, it's warm, but you're going to be okay because your skin can block it. Okay? So alpha particles, they're a helium nucleus. Some properties of alpha particles, they move slowly. They're really big. But they are ionizing, meaning they are positively charged. This is important. An alpha particle is positively charged. It has 2 protons and how many electrons? None. It's just the nucleus. So if you're just a nucleus with 2 protons, you're cruising around and you bump into an atom that has electrons, guess what happens? Zoink, yeah. You take the electrons away and you become not a helium nucleus, but a helium atom, which floats away. See how this works? The alpha particle is a helium nucleus, but no electrons. So it's like, boop, ba-doop, 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 boop, hey, bump. I'm going to steal 2 of your electrons, and I'm not going to be the helium nucleus anymore. I'm going to be a helium atom. Whee! And off I go into space. The problem was that atom that used to have 2 electrons, or used to have some electrons, just lost 2 electrons. That's called ionizing. You turn that atom into an ion. Does that make sense? Hang in there, Aaron. Hang in there. You can do it. Oh, he's already asleep. Okay. Anyway, so atoms function, and there you go. Atoms and elements function normally.
I closed my eyes.
If your cell is expecting an atom and it gets an ion instead, that ion doesn't do what the cell needs it to do. Does that make sense?
Yeah.
So ionizing radiation will destroy atoms. It will destroy you. Don't swallow ionizing radiation because it will kill you from the inside out. But if you're like holding some in your hand, you're like, no. Okay. Give me a thumbs up if you're happy with ionizing or alpha particles. If you have questions, raise your hand and wave it around. Okay, now, if alpha particles are big and slow and don't really do much, then there's beta particles. Beta particles are high-speed electrons. These are the athletes that just punch right through the line. Red Rover, send Andrews. On the no one. Andrews is gonna be the last call because he'll just bust right through anybody. Okay. So, a beta particle is a high-speed electron ejected from the nucleus. Now, beta decay is really interesting because what is the charge of an electron?
Negative.
It's negative. The charge of an electron is negative. Now, the reaction, the equation, still has to balance. 131 still has to equal 131 plus 0. And 53 still has to equal 54 plus -1. So by ejecting an electron from the nucleus, look what happens to the atomic number. The atomic number goes up. By ejecting an electron, the atomic number goes up. By ejecting an electron, the atomic number goes up. Why? Why does it do that? 1 then 2.
Well, because since they're losing an electron, it changes the negative charge to a positive charge.
Close.
Or a neutral charge to a positive charge.
Exactly. Okay, did you guys hear that? Andrew, is that what you were going to say? We do? Okay. So yeah, by ejecting an electron, a positive charge is created from a neutral charge. So imagine this. You got a neutron. A neutron has a mass of, this is for you, neutron has a mass of 1 and a charge of 0. And a proton has a mass of 1 and a charge of
Plus 1.
plus 1. And an electron has a charge of, or mass of
0.
0 and a charge of
-1.
-1. So those are our 3 primary subatomic particles. Imagine you did this. Then could you then say a neutron minus an electron equals a proton?
Yes.
Could you do that math? Is that a valid math?
I don't know.
I mean,
Okay.
well, yes, it technically is.
This is what it basically means. When a neutron with a mass of 1 and a charge of 0 spits out an electron, that electron leaves the nucleus as fast as possible because are there electrons in nuclei? No. Electrons are not in the nucleus, they're somewhere else. So the electron that comes out at extremely high speeds. Boop. So when a neutron boop, leaves the electron, kicks out the electron, that neutron morphs into a proton. Because you can think of a neutron as a proton and an electron together. So when the neutron kicks out an electron, a proton is formed.
Oh.
Does that idea make sense?
Yeah.
So that's why the overall nuclear charge goes up. The mass doesn't change. A neutron is a mass of 1, a proton is a mass of 1, but the nuclear charge increases because the neutral particle becomes a positive particle.
Wait,
No, but you can look it up on YouTube.
no.
Okay, so a neutron has a mass of 1 and a charge of 0. So when that neutron becomes a proton, its charge goes up by 1 because the negative charge gets ejected. Neutral minus a negative 1 becomes positive. 0 minus minus 1 becomes
Positive.
plus 1. Capiche?
Yes.
Okay, so that's beta particles. Some properties of beta particles, they move extremely fast, pretty close to the speed of light. They can penetrate you and me. They will get stuck in your bones. They will get stuck by concrete or metals. You guys know your bones are metal, right?
They're metal.
Yeah, your bones are mostly metal. Yeah, all that calcium.
Yeah.
Calcium's a metal.
That makes sense.
Well, they replaced the calcium in his body with adamantium. So something very similar happens when you brush your teeth. You're replacing a few of the calcium atoms with fluoride ions. Never mind those. Ignore that. So if you brush your teeth with adamantium, you'd replace your calcium with adamantium. Then you'd have adamantium teeth. Okay.
It's not one.
If you are comfortable with beta particles, give me a thumbs up. If you want to talk about them more, raise your hand. Okay, yes.
No, actually, I'm good.
We're good? Okay.
Wait, just
Okay. Now, alpha is the Greek letter A. Beta is the Greek letter B. The Greek letter C is not kappa. The Greek letter C is gamma. Gamma decay are spare change. Okay. This is what turns Bruce Banner into the Hulk, and Peter Parker into Spider-Man.
Are you serious?
Well, Peter Parker needed a spider. But, so, gamma decay, are you serious? No. No, I'm not. So, gamma decay is the spare change that happens when nuclear decay happens. Okay? It has no mass. It's just high energy spare change. That's all it is. Just high energy spare change. So, for instance, this is the reaction you learned about alpha decay. I didn't show the gamma particle in there, but this is what really happens. The uranium atom, I don't know why the animation is so wonky and fast, but the uranium atom turns into thorium and an alpha particle, and 2 photons of gamma particles, of gamma radiation. Pew pew, they're like lasers. Pew 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 pew. Red Rover, send the laser right over, pew, right through you, at the speed of light. Pew. If you want to know what that feels like, I have my laser engraver in the other room. You can put your hand under it. It won't go through you. It's not powerful enough to go through you. But it will burn you. You're like, give me I want a Boulder City tattoo. You can do that. You have to hold your hand really still for about half an hour. You can do it. You want to touch it? We'll fire it up, but it'll be like, hey, it's hot. That's about it. Okay. We are almost done with today's lecture. Any questions so far? So, okay, question.
so is it just extra? Or
Yes. It is
Like, does it
spare change. It just keeps going. It blasts right through stuff. So because imagine it, think of it as a sci-fi laser. When a sci-fi laser hits something, it punches a hole in it. That's what a gamma particle does. When a gamma particle hits something, it punches right through it.
Is lead the only one that can slow down?
Yeah, lead is, the particles are very, very dense. The nuclei of lead is very, very dense. And because it is so dense, it can absorb a lot of energy. So the gamma particles go, they slow down, and eventually they stop.
So like, okay, so like in a nuclear explosion, it's a lot of gamma radiation. That's why like Indiana Jones, the example of survivors, the lead line.
No, yes and no. Lead line things will slow down and block a lot of radiation. But if Indiana Jones was in a refrigerator near a nuclear blast, he would still get blasted with way more than that refrigerator. It's kind of like this. Yeah, essentially. So you know what kills you in a naval battle? If you were in like a 200-year-old naval battle, you know what kills you? It's not the cannonball. It's the wood shrapnel that the cannonball hits. Does that make sense? So what kills you in a nuclear reaction is not the nuclear reaction, it's all the particles that are launched from the particles that get hit.
It's the radiation, right?
The radiation and the shrapnel.
Wow, that's actually okay. I don't know why.